In this video, we're going to look at a simple application of second-order linear homogeneous ODEs with constant coefficients. This application is that of the oscillation of a pendulum. What we will note is that the oscillation, that is the angular displacement of the pendulum, is described by a second-order ODE. A pendulum consists of a concentrated mass m, a distance L from the axis of rotation. The ODE is obtained by noting that taking the sum of the moments about the axis of rotation p is equal to the mass moment of inertia multiplied by the angular acceleration alpha. Now, if you haven't studied dynamics before, that is okay if you don't understand this particular equation. The derivation is not really what we're shooting for in this video. Nevertheless, this leads to the ODE given here, which we are going to try to solve in order to obtain the angular displacement as a function of time. So for those who have studied dynamics before, you will recognize that this is our mass moment of inertia. This is the angular acceleration alpha. And this is the net moment about point P, which we note that the only force exerting a moment about point P is the component of the weight perpendicular to the moment arm L. We note that the mass appears on both sides of the equation, so we can get rid of that, as well as one of the length terms. This gives us a simpler or a simplified equation. L dt squared, d squared theta by dt squared, is equal to the negative of g sine of theta. Now recall that the methods we derived for second-order ODEs apply for linear ODEs. However, we have this pesky term over here, which is a nonlinear term for the dependent variable theta. We can linearize this term by noting that for small angles of theta, we can say that sine of theta is approximately equal to theta itself. So substituting this small angle approximation and rearranging our ODE, we are left with L d squared theta by dt squared is, or rather, plus g theta is equal to 0. And now we have a second-order homogeneous linear differential equation with constant coefficients L and G. Now recall in our derivation of the characteristic equation, we proposed that the solution is of the form y is equal to e to the mx. Now we're going to avoid using the exponent m because m appears as the mass for our pendulum. So what we're going to say is that we are seeking a solution for theta, which is of the form e to the rt, where now t is our independent variable instead of x. The characteristic equation will therefore be of the form lr squared plus g is equal to 0. So solving for r, we find that r is equal to plus or minus I multiplied by the square root of g over L. So recall that this is the third case that we looked at for our characteristic equation where we have complex roots. For complex roots, alpha plus or minus I beta, we said that the solution will be of the form e to the alpha t multiplied by c1 cosine of beta t plus c2 sine of beta t. Note that the roots of our equation, we have alpha is equal to 0 and beta is equal to the square root of g over L. This tells us that the general solution for our equation will be e to the power of 0, which is just 1. So we just have c1 cosine of the square root of g over L multiplied by t plus c2 sine of the square root of g over L multiplied by t. So this is the solution to our second order linear constant coefficient ODE, which describes the oscillation of our pendulum. This yields some very interesting results. Notably, the frequency and period are independent of the initial angular displacement. That is, we don't have any terms that depend on some theta naught, for example, in the frequency. So whether we displace it 1 degree or 5 degrees, our frequency omega will be the same. Similarly, the period t will be the same. All simple pendulums have the same period regardless of their initial angle or their mass. The frequency, omega, which we'll call omega naught, is equal to the square root of g over L. And the period will be equal to 2 pi multiplied by L over G. The fact that the period remains approximately constant regardless of the mass or amplitude of oscillation is the reason pendulums are so useful for timekeeping. So this was a simple example of the application of a second order linear homogeneous constant coefficient ODE.